So let's continue. So we are going to talk about topic sampling. Actually, there are many techniques for sampling. The first one is sampling using delta signals. That is using series of delta signals. The second one is called flat top sampling. And the third one is first one using delta signals, second flat top sampling, and third one is natural sampling. So first one using delta signals. Here for sampling of analog signal we use delta signals. So samples are taken like this. Okay. Now in case of flat top sampling, as the name tells or suggests, the top here of sampled signal will be flat. So this will be like something of this type. Okay. And obviously from the name tells natural sampling. Natural sampling means the top will be same as the analog signal. The top of the sample will be same as the analog signal. So clearly one can say that for flat top sampling, what we should do is we should take a rectangular pulse and convolve with the original analog signal, that is xt. Okay. And what our mind tells is for natural sampling, similarly we take a pulse rectangular and simply we should multiply it so that its amplitude will take the form of the original analog signal. Okay. So let's continue with the first one, sampling using delta signals. So we have a simple signal xt. So its Fourier transform will be x omega. And for converting it into sampled signal, this is also called ideal sampling. Okay. So for sampling it, we have to multiply this signal by a series of delta functions. That is the resulting sampled signal y delta t. We can say y delta t will be xt multiplied by summation of delta t minus k ts. Let's say this timing will be ts to ts and so on. So summation delta t minus kts, k is equal to minus infinity to infinity. Okay. So if we will look at this in frequency domain, so it will become y delta of j omega is equal to xj omega convolve with summation when we will convert it into frequency domain, it will become 2 pi ck of this series of delta function multiplied by delta omega minus k omega omega s. Okay, from minus infinity to infinity. Okay. And when you will find the ck values for the Fourier series coefficient values for this train of delta function, you will find that ck for this series of delta function will be nothing but simple 1 upon ts, sampling time, that is fs. Okay. Okay. And here it will be like 1 upon 2 pi Okay, so y delta j omega will be, this will cut here and it will become summation minus infinity to infinity ck times x of j omega minus k omega s, right? Because x omega into delta omega minus k omega s is equal to x of omega minus k omega s. Okay, okay, so let's proceed. So what we can see from here is, if we have x omega is something like this, band limited to b hertz, or we can say in radians, that will be 2 pi b radian. Okay, so let's take omega. Simply, for simplicity, we are not going in frequency. Okay, and this is x omega, right? So when we will plot y omega or yj omega, both are same, of delta sample signal. So we can see here, if we will expand y delta j omega is equal to summation minus infinity to infinity ck x of j omega minus k omega s. When we will expand this, this will go something like this: c0 x of j omega plus c minus 1 x of j omega plus this will be something like this: j omega plus omega s plus c 1 times x j omega c1 of x times j omega minus omega s. Okay, so its diagram will be something like this: the same x omega at baseband, this will be 2 pi b minus 2 pi b, and its shifted version, shifted by omega, amount of omega s, right? So it will be something like this. Okay, and similarly it will and it will be scaled by c0. This will be scaled by c1. Here it will be minus omega s, and this point will be minus omega s plus b, and this will be minus omega s minus b, this point. Similarly this point will be omega s minus b, and similarly this point will be omega s plus b. Okay, so we can see that if this point will go beyond this point, then overlapping will takes place in frequency domain, and we cannot exactly we cannot get the original signal back. So for to get the same signal, so we will use a low pass filter of this much bandwidth. And what we will do is, we should take omega s minus b 2 pi b, sorry, omega s minus 2 pi b should be greater than equal to 2 pi b. So from here comes omega s should be greater than 2 times 2 pi b, that is message bandwidth, or fs should be greater than equal to 2b, that is nyquist criteria of sampling. Nyquist criteria of sampling. Okay, so this is what ideal sampling. To recover this type of sampling, we simply put a low pass filter of bandwidth 2 pi b in terms of fs, if we want to write, and in case fs is equal to 2b, we can write the low pass filter bandwidth to be equal to 2 pi b or 2 pi fs by 2, that is pi fs. Okay, so for flat top sampling, see my next video. Thank you.